everyone. I am Vineet Kumar Sinha from ABES Engineering College, Ghaziabad. In this video lecture series, we are discussing the subject Materials Engineering. And in unit, we are discussing Unit 5, which is Non-Destructive Testing. And today's topic of discussion is material behavior at a very low and very high temperature. So, as per the syllabus, we'll be covering this topic, material behavior and pore properties at a very low cryogenic temperature and material behavior properties at a very high temperature. So first, the very low temperature, that is cryogenic temperature. The term cryogenics, has generally been used to refer to temperatures below approximately minus 150 degrees Celsius. According to the laws of thermodynamics, there exists a limit to the lowest temperature that can be achieved, which is known as absolute zero or minus 273.15 Kelvin. Minus 273.15 degrees centigrade or 0 Kelvin. Material behavior at very low temperatures is cryogenic. The effect on mechanical properties would be brittleness. At extremely low temperatures, material become increasingly brittle due to reduced atomic mobility. So brittleness would be increased and ductility would be lesser. This brittleness can lead to unexpected fractures under mechanical stress. Similarly, decreased ductility and toughness. This always goes opposite to each other, brittleness and ductility and toughness. Ductility and toughness decrease significantly as the temperature drops. This reduction in ductility can result in catastrophic failure under relatively low stresses also. So less than the UTS or yield stress, this will fail under very low temperature ranges. Increased strength, despite reduced ductility, despite the ductility will get reduced, the strength of some material is observed may be increased at cryogenic temperatures due to decreased thermal agitation of atoms. Since the thermal agitation of atoms becomes less, so the strength gets increased. Now, what about thermal properties? What are the changes in thermal properties at very low temperature? Thermal conductivity. The thermal conductivity of material decreases. Thermal conductivity of material decreases at cryogenic temperatures due to the reduction in lattice vibration. Lattice vibration would be reduced and hence the thermal conductivity of material decreases. This can impact heat transfer rates and further thermal insulation requirements. Specific heat capacity decreases as temperature decreases, affecting the amount of heat required to raise the temperature of a material. Since the specific heat capacity gets decreased as the temperature decreases, the amount of heat required to raise the temperature of material is affected. Thermal expansion. What is the behavior of thermal? What is the cause of thermal? Result of thermal expansion? What of the thermal properties of the lower temperature? Use an application at very low temperature. Materials may exhibit significant changes in thermal expansion coefficients at cryogenic temperatures, leading to dimensional instability and stress. What are the material selection considerations for very low temperature application? Low thermal expansion coefficient. Materials with low thermal coefficient of expansion are preferred to minimize thermal stresses. Similarly, high ductility and toughness materials should be chosen. Selection of materials with high ductility and toughness is essential to prevent brittle fracture at low temperatures because brittleness gets increased Resistance to embrittlement. Avoidance of material prone to embrittlement or caustic embrittlement or phase changes at cryogenic temperature is crucial. So the selection can be made as considering the factor. Thermal insulation. Consideration of thermal insulation materials and techniques to minimize heat transfer and maintain cryogenic temperatures. Now coming on to material behavior or property at very high temperature, how it behaves. So first we should observe creep behavior. At higher temperature, creep is very effective, very significant. So creep behavior should be analyzed. So creep deformation is the time-dependent deformation of materials under constant stress at high temperatures. This we have already seen in our previous lectures. Materials exhibit significant creep behavior at temperatures above a certain threshold, leading to dimensional changes over time. So there is a significant creep behavior at temperatures above a certain threshold, that is nearly equal to 0.4 Tm in Kelvin, which we had seen earlier, or greater than equal to 0.4 Tm, where Tm is in Kelvin, and Tm is the melting temperature or melting point of that material in Kelvin. The creep rupture. Second, after deformation, this creep failure or creep rupture. Creep rupture occurs when a material fails under sustained loading at elevated temperatures, resulting from the accumulation of creep deformation. Then after creep rupture and creep deformation comes the oxidation and corrosion. So increased reactivity happens at higher temperature. Materials exhibit increased reactivity with oxygen and other gases at high temperature, leading to oxidation and corrosion. So there must be some counter arrangement should be made by selecting materials towards this oxidation and corrosion. Oxide scale formation. Oxide scales form on the surface of materials exposed to high temperatures, which can reduce mechanical properties and accelerate material degradation. Can reduce mechanical properties, and also oxide scale formation can accelerate material degradation. So we have to be very careful about this while selecting material for high temperature applications. Similarly, corrosion will also be a problem. This will also get increased. Corrosion rates may increase at higher temperatures due to enhanced chemical reactions, impacting material integrity and performance. Now, the effect on thermal expansion and contraction of high temperature. Differential thermal expansion. Materials expand and contract significantly with temperature changes, leading to differential thermal expansion between materials. This can result in thermal stresses and dimensional instability. So for design, to avoid this, the design considerations are designing components with thermal expansion joints, having thermal expansion joints to facilitate easy movement, and considering material compatibility and essential to mitigate the effects of thermal expansion and contraction. Phase transformation, this should also be avoided. Phase transformation, changes in material structure. Materials undergo phase transformation such as melting, solidification, and recrystallization at higher temperatures, resulting in changes in material structure and properties. So phase diagram should be understood properly. Understanding phase diagrams and transformation kinetics is crucial for predicting and controlling material behavior at very high temperatures. We should focus on design consideration should be made on differential thermal expansions also, phase transformation, and phase diagram study of phase diagrams also. Material degradation mechanisms at higher temperatures, grain growth. Why material gets degraded fast at higher temperatures? Due to grain growth. Grain growth occurs at higher temperatures, leading to reduced strength and ductility in materials. Again, embrittlement is a factor. Embrittlement due to segregation, precipitation, or diffusion of impurities can occur at elevated temperatures, reducing material toughness and resilience. Similarly, thermal fatigue results in from cyclic heating and cooling, leading to cracking and failure of materials exposed to high temperature fluctuations. So this was all about the unit 5, that is non-destructive testing and behavior of materials, behavior and properties at very low cryogenic and very high temperatures. And this was all about the unit 5. Well, we'll discuss further units in our subsequent videos. Thank you.